local organizer, Matty, and all the organizing team for bringing me and everyone, right, to this really beautiful city. It's my first time coming to Finland, so I have been really enjoying the trip so far. So today I'd like to report to you about, our research on one specific area, within the research field of flexible sensors, that is a design of bioelectronics. And in particular, I will talk about mostly about how we can design the materials and devices to incorporate two new properties onto bioelectronics, mainly by using polymers as the key functional material. One property is about adhesive property to tissue surface, and then the other is a so-called immune compatible properties. So overall, when talking about bioelectronics, one big application direction is try to design the electronics that can interact very intimately with our human body. So it has been driven by the emergence of several big application directions. For example, precision medicine, Internet of Things, and if you take our human body as a very important things, there is Internet of Bodies, and also human-robot collaboration, human-machine interfacing. So for all these application directions, one challenge that we are faced with is the significant mechanical property mismatch. Like the current electronics is very rigid and brittle with the human body that is often soft and constantly moving. So then what we have started to think and would need to solve for the challenge is to basically redesign the electronics to mimic the properties that are very common from human body or biological systems broadly, so as to achieve the intimate integration and then even eventually seamless merging of the two to operate cooperatively together. So overall, when talking about biological systems, which are made by the structures across a very large range of length scale, so they often have some common features. For example, like biological tissues and organs, they are very soft and constantly deforming with a dynamic motion. And also between different parts of organs and the bones, there is also very stable adhesion in between to keep everything as an integral structure. And a lot of the biological processes are driven by biochemical reactions with a high specificity. So those are some common features at the underlying level. And then if we take a look at a level that is a little bit up, like a subsystem level, there are a few very distinct systems driven the overall function of biological systems. For example, our nervous system, like the brain, it is in charge of all the intelligent information processing for each of us. And also we have immune system, which is serving as the main mechanism that is protecting us from having like an infection, from diseases, from all the different kind of invaders. So then basically what our research has been focusing on is to take these features of from biological system as the main inspiration to drive us to design new type of functional materials, mainly based on polymers, as I mentioned before, and also devices to combine the advanced electronic photonic properties that can give the functions across the sensing of the different modalities and the computing, especially the computing that mimic the function, the operation of a brain, and to the different kind of modulation, like biostimulation functions. And then to benefit from having the biomimetic properties and the biomimetic operations, and then eventually to realize continuous, efficient, and long-term stable acquisition processing of health data. So today, I'll only get to talk about the first parts, mostly about the work we have been doing regarding the sensing functions, but won't really have time to touch upon the other two parts, the computing and the modulation is mainly our design of a stretchable light emitting diode, stretchable OLED. So if you have interest, you can look at the papers we recently have published. So overall, for the sensing, the main motivation that has been driving our research is to design like a better performing and a more effective bioelectronic sensors. So then to do this, our thought process actually started from what's really defines what is a better bioelectronic sensing. So overall, we all know that for the sensing function, it comes from the starting point is to get the different kind of biosignals from the tissue tissue surface. And then eventually the ending point is we want to get electrical readouts that is correlated to the biosignals. And then from this, a better bioelectronic sensor usually means the electrical readouts can have high signal noise ratio. So this is usually where we want to get to. So then the question is how we can get there. So what we have been thinking is for this, there are actually two main steps. The first step is the signal has to come from the tissue to be received by the sensor. Right? It seems to be trivial, but actually it's very important. If the signal is not get onto the sensor, then sensing cannot happen. So this is the first step. And then the second step, of course, very obviously, that is the function of the sensor that's further transduce the signal to electrical readouts. So then a more effective bioelectronic sensing comes from optimizing both of these two steps. And then for the second step, very obviously, it's mainly determined by the function, the performance of the sensing device, especially from the aspect of having higher sensitivity. That has been already attracted a lot of effort of the sensor community to work on. So then what we have been mainly looking at is the first step. That highly relies on having a conformable interface, right? The interface is key between the device and the tissue. So the goal is try to have the interface with a minimized distance and the impedance so that the signal decay that can possibly have at this interface can be minimized. So this is what we have been trying to do in our research. So then, the next thing we did is to take a further look at the property of the interface. So the interface basically large come from the property of the tissue or organ. For example, the brain that is very curvilinear of the surface, and also the heart, right? So constantly beating with a lot of tissue deformation. So then if we think about the device that we have been having from the silicon industry to interface with those tissues, basically, those device often starts with a very rigid mechanical property. And then what's the issue? The issue at the beginning is it cannot do very well for conforming to this kind of a heavy curvilinear surface. So then usually, if you don't do anything of the conventional device, it can only make a loose contact, right? With always leaving gap in between. So this is the beginning. And then if you are trying to do chronic function, then over the period of months and years, another major issue will come up. That is at this interface, foreign body response, immune response will start to kick in, and then leading to the growth of thick fibrotic tissue. So this is further increasing the interfacial impedance. So this is conventional device. And then in comparison to this, the question is what would be the more ideal kind of device? So then what we are thinking is first, the device need to have a much softer and like a tissue compatible mechanical property to form the conformable contact at the beginning. And also the tissue is deforming like the heart. This conformable contact also need to be maintained well during the deformation of the organ tissue. So then to achieve this, it has already required actually two mechanical properties to act together. So first, very obviously, this has already attracted tremendous amount of effort. That is to achieve mechanically stretchable property to accommodate such level of deformation coming from the organ or tissue. But only being stretchable is not enough because the deformation is coming from the tissue side. Then you need to make sure the device can follow, right, without delamination. So that would require another property that is having stable attachments like a tape, right, at this interface. So that's what we call bioadhesive. So this two coupling together might be able to solve the challenge for the beginning stage. And then we still face the challenge of the chronic implantation for this longer period. So that would require another property to minimize the growth of the fibrotic tissue, which need to come from having the compatible design with our immune system, so that the immune reaction triggered by the foreign material can be much more suppressed. So those are the three aspects that we have started to think about. And then to work on this, we need to pick like a sensing platform and the material. The one that we have been choosing to work on so far, it's a new type of transistor. So in the morning, from the plenary talk by Professor Thing, we have already learned about the recent progress in field effect transistors. This is a different kind of transistor, so-called electrochemical transistors. The key distinction is the gating mechanism. Here, the gating is through redox reaction that happens across the entire thickness, entire layer of the semiconducting channel. So this is enabled by the semiconducting polymer to have not only semiconducting property, but also can allow the transport of ions into the entire bulk volume. So then what's the benefit? The benefit is that when this type of transistor working as an amplifying or sensor device, this volumetric gating mechanism can greatly benefit to have a much larger capacitance of the gating. So then this larger capacitance will further increase the transconductance, which is the key device figure of merit for the amplification capability. So then when using this as a biosensor, it usually can give much higher sensitivity and also with a lower operation voltage. And it can be used for bioelectrical sensor and also biochemical sensor. One example that we have shown this is from the work that we utilize this semiconducting polymer, redox active conducting polymer as a channel layer. And by functionalizing the side chain of the semiconducting polymer covalently with the protein, it's the enzyme for glucose, just directly functionalize onto the side chain. Then when we use this semiconducting polymer as a channel layer in the so-called OECT, it can have the high sensitivity and the specific sensing function for the presence of the glucose. So as you can see from this performance. So basically, from this, it gives the implication that's the key material that we need to engineer to work on for having better interface with the tissue. It's really this redox active semiconducting polymer. Okay, so to focus on this, actually we have made several steps. The first step actually came back to the first property that I talked about. It's a stretchable property. So for this, we honestly actually didn't do too much in designing new material. It's a pretty conventional design for this redox active semiconducting polymer. The only distinction that we identified based on the hypothesis of the mechanical property for the design is to choose a unique, like a backbone architecture to have a so-called asymmetric arrangement of this Sihong unit to weaken the interaction, the pipette stacking between the backbones, so that because the pipette stacking will have some non-overlapped orientation. So then this helps this polymer to be able to very effectively dissipate the stretching you are applying in the way that the sliding between the different polymer chains can happen. So this enables this design to be able to, this polymer structure to deform to the stretching level of 200% strength. It's 3 times of the original length without forming any crack. And then using this polymer, we further made it into a fully stretchable OECT-based electrophysiological sensor. And we have demonstrated its use on the deforming, like a raised area for measuring the ECG signal, electrocardiogram. And then because of the stretchable property, even when the race is deforming, the recording function is not really getting affected. Okay, so this is showing what stretchable property can help us. But when I previously showed these results, people often ask me one question: how do you attach it? And honestly, we didn't use anything that is fancy or high tech. It's very like a simple way to attach the device. I'm not sure if you can tell from the picture. If you cannot, I can further zoom in. So it's by using like 2 pieces of tape at the 2 ends of the device. So this can work overall, but it's not optimal, because at the middle part of the device where the sensing really happens, you can probably see there's still a gap in between, right? It's because the device intrinsically doesn't have the adhesive property to the skin surface. So this actually reflected like a common challenge has been faced by almost any kind of bioelectronic or wearable devices when making into a like a thin sheet kind of form factor. Is how to attach. So usually people have to use one of these 2 conventional approaches. The first one is like what we were doing by just attaching device around the edge, like for example, by using tape or by using surgical suturing. So for suturing in particular, it will also cause like additional tissue wounding, like being more invasive. And another possible approach is to add adhesive there that is not electronically conductive at this interface. So then the results, the disadvantage is further push the device away from the tissue surface and increase the interfacial impedance. And then this, for these two strategies, it is particularly not so compatible with like OECTs for tissue interfacing, because as I've shown earlier, the part that's really give the sensing function is a semiconducting channel. You need to have the channel to be able to receive the signal. So then that's made us to start to think about whether we can utilize material design of the semiconducting polymer to make it to have intrinsic direct adhesion property with the tissue surface, so-called bioadhesion. So then if that's possible, then maybe it can make the semiconductor and the further the OECT-based sensor can be attached onto the organ or tissue surface, just like a piece of tape. So then how can we do this, right? This is a question. Actually, the idea is showing in this schematic. So, our starting idea is very simple. So basically what we want to do is to combine two properties, semiconducting property and the bioadhesive property together. Then why don't we just use the two different polymers and then mix them together? Then maybe they can, each one still providing their own properties to make this a bioadhesive semiconductor. So then my students Nan started to try this out. But actually, long story short, after several iterations of the design, eventually it's turns out that the design of the bioadhesive polymer for one of the two parts is really the key to make this work. Working especially by having the right type of blending morphology, so that one property is not sacrificing the other. So the main design that my student and I has came up with is to have this brush kind of a structure for this bioadhesive polymer. So basically, it has several design features. First is at the end of the side chain, it needs to have the functional group that can form the covalent and the non-covalent interaction with the tissue, like with a protein or peptide in the tissue, on the tissue surface. This is what really gives the adhesion property. And then for this, for attaching, for grafting these groups onto the side chain, another key is to introduce this long extender of the side chain to make it into brush. The reason is that this has to be blended with this kind of design of semiconducting polymer, which usually has a very long side chain for the processability and also ion conducting property. So then this gives a competition of which side chain end gets to expose on the surface. If this side chain is not long enough, then you can imagine it could get shielded by this longer side chain. So then to win this competition, we had to extend the length of this side chain to be even longer. That's what gives to this brush architecture. And then this design also gives a water absorption property because of the hydrophilic nature. So that's on the wet tissue surface, like a physiological biological fluid can be temporarily removed from the absorption of this polymer, similarly to a piece of a sponge. So that's the surface can be temporarily dried, and then also have the desirable mechanical property. So then eventually with this design, what we did is to utilize these two monomers as a starting material to blend with the semiconducting polymer into the same solution. And then with these still being in the monomer state to spin coat into a thin film. Then in the thin film, there will be some level of phase separation, but the monomer can help to minimize, reduce the phase separation scale. And then afterwards, after forming the thin film, then we further cross-link this bioadhesive polymer under UV exposure. So eventually that is giving us this kind of a morphology as shown by the AFM images. So the semiconducting polymer on the two surfaces is forming very dense nanofiber structure with like a continuous percolation. So basically this makes sure the transport property, semiconducting property, is not getting affected by blending into the bioadhesive polymer. And we indeed have tested in the OECD that the semiconducting property is not sacrificed at all. And then at the same time, because the bioadhesive polymer is serving as an overall matrix, then we think this can further enhance the bioadhesive property for this semiconducting layer. We have further verified this by utilizing the peeling test, the T180-degree peeling test, to test the adhesion property of different kind of films on the tissue surface in the wet state. So the result shows that compared to the neat semiconducting polymer, after blending with this bioadhesive polymer, then the bioadhesive semiconductor we got has the adhesion toughness enhanced by over 50 times. And also we have expanded the test onto different kind of tissue surface and also skin. They all showed like a similar level of adhesion interfacial toughness. Okay, so this showed this design for the adhesion property basically has worked. And then finally, for utilizing this really onto the sensing functions, we have further made it into a fully bioadhesive OECD-based sensor that has not only the exposed semiconducting area, but everywhere of the device surface have the adhesion property. So this basically enabled the sensor to be able to attach onto the surface of a rat part in a ex vivo epicardial recording experiment. Let me place the video again. By just a very brief and gentle finger pressing. And then after that, during the beating of the hearts, you can see the device is maintained very stable, not drifting away. Even we try to test with like additional mechanical dragging force, it's still maintained very stable. It's not influencing the recording signal quality as well. And then in comparison, if we make the like a very similar kind of a sensor, there's a different video. The only difference is the sensor doesn't have the surface adhesion property. Then although initially it can still like get adhered attached onto the hard surface from the capillary force, but it's not stable at all, right? When there is dragging force, it starts to drift away and then eventually got fully detached. And then you can also see the big influence on the recording signal quality. Okay, so hopefully this is showing how tissue adhesion property could help the flexible sensors like bioelectronic sensors to have stable interfacing property with the tissue that's bioelectronic devices. But this still didn't solve all the challenges. This is because, as I mentioned earlier, for any kind of implantable devices, foreign materials, they all face one common challenge, that is foreign body response from the reaction of our immune system. So basically what happens is once a foreign material gets into the human body or animal body, this process will be, series of process will be triggered that started from having the non-specific absorption of proteins and cells in a so-called biofouling. And then that will lead to the deposition of a different kind of immune cells like macrophage, monocytes, neutrophils, which will further lead to a cascade of cell signaling process, and then eventually ending up with the encapsulation, like a deposition of a fibrotic tissue, collagen, or you can also call it scar tissue. So then this is creating like a number of challenges or problems. First, it's of course, a persistent inflammation reaction to the host of receiving this implant. And also for the recording, the sensing function is increasing the interfacial impedance further. That leads to the decreased signal amplitude. So this, is even like a challenge for the so far the most acceptable, widely used implantable device. That's a pacemaker. So I'm not sure if our audience know, actually for 10% of the patient receiving pacemaker, they would experience like complication from the foreign body response only in the first months of the implantation. That would lead to the need of a secondary surgery within the first months to reimplant with a new pacemaker, right? So this is basically reflecting the challenge coming from the foreign body response. Actually, in the biomaterials community, like those people designing material for tissue engineering, drug delivery, there has already been a very large volume of research to address this challenge by designing new kind of biomaterials and also try to get more immunological understanding of the foreign body response. So what we want to do for the bioelectronic device is to take those as the guiding knowledge and inspiration to lead us to design new kind of a semiconducting polymer that can have the desirable immune-compatible chemical or physical properties to have much more suppressed foreign body response. Okay, so the first aspect is the chemical property. As I mentioned before, a lot of progress and understanding has already been made. For example, people have shown that on hydrogels, if you utilize like some very special sidechain units, for example, this is a so-called pyrene, this is Sihong, they all linked to this triazo unit. They will provide some active immune modulatory effect to greatly suppress the level of foreign body response from this hydrogel. And in other examples, people have also shown using this very unique kind of polymer structure, so-called zivotonic design, having both cation and anion charges in the covalent structure, it can offer a super hydrophilic property so that the biofouling can get significantly suppressed, so-called anti-biofouling. And also, even at the elements level, there are some very special elements have the active immune functions. For example, this element, selenium, that is an element that's all the animal bodies, like human bodies, are having. And then people have also found that this selenium is not only biocompatible, but also have immune functions. For example, it has been utilized in the design of cancer treatment drugs. So then what we have been thinking is whether we can utilize these designs to incorporate into the design of semiconducting polymer in a certain way that they can still provide the immune compatible functions, but not influencing the semiconducting properties. So then that drove us to start the work, still going back to this design that we have been working on. So to incorporate the immune compatible units. So basically the idea we came up with has two aspects. The first aspect is about the backbone of the semiconducting polymer, which is the most distinct feature of this so-called conjugated polymer. So what we wanted to do, as I mentioned earlier, is not to sacrifice the charge transport. But for conjugated polymer, the charge transport is mainly determined by the backbone structure from having this like a pi conjugated unit. So then the idea we came up with is to utilize a different kind of conjugated units, like a pi aromatic unit, to incorporate this selenium, which is in the same group with a commonly used aromatic unit that is sulfine, so that the conjugation can still be kept, but it could possibly benefit having the immune compatible, immune active property of the selenium. Right? This is our first part of the idea. And then we also took a look at the sidechain structure by directly attaching, like grafting some of the immune modulatory groups at the end of sidechain, and then with a hypothesis that they could provide similar effects on the sidechain for the immune compatible functions. Okay, so after synthesizing this polymer again by my student Nan, we have implanted in the mice through subcutaneous implantation, and then after 4 months to take it out, and then do the tissue analysis surrounding the implant. So to characterize foreign body response, what we are really comparing is where this arrow is pointing to. There's a blue structure that is showing the scar tissue. And then the result is showing first, if we utilize the selenium to replace sulfur in the backbone, only in the 1/3 of the ratio, it can already decrease overall collagen density by about 50%. Okay, and then after that, if we further attach those immunomodulatory groups on the sidechain, it can further help to decrease the foreign body response to the level compared to the control polymer by about 70%. So basically, this is showing these designs can work conjunctly together in the way that we want. But actually, for these designs, especially selenium, although people have shown it's an immune active function in cancer treatment, none of the research, to the best of our knowledge, it has been used for suppressing foreign body response. So then we further have carried out, more in-depth tissue analysis, like an immune characterization, to understand what is the underlying mechanism. The key immune cell that we have been focusing on is a macrophage as key mediator for the foreign body response. So overall for macrophage, it has two important phenotypes. One is so-called pro-inflammatory, so-called M1, and the other is anti-inflammatory. And then each type will secrete different kind of cytokines that reflect the activity of the macrophage on these two phenotypes. So then what we did is to utilize ELISA to measure the level of the secreted pro-inflammatory and anti-inflammatory cytokines from these four different type of polymers. The result here is showing for the pro-inflammatory cytokines, they can all get downregulated across the board by these three newly designed polymers. And then at the same time, they also upregulate the anti-inflammatory cytokines. So basically, this means for these two kind of design, one is a selenophane with the reactive oxygen species scavenging property, and also the side chain with the immunomodulatory function. They all can go to the direction of making the macrophage to behave less pro-inflammatory, but more anti-inflammatory, and then eventually suppress the foreign body response. Okay, so and also quickly, we have checked the electrical property in OECT, and also showing these three new designs compared to the control polymer had the charge carrier mobility and transistor performance stay at a similar level. Okay, so this is kind of our first work about the chemical property. But the chemical property is only one aspect for foreign body response. Mechanical property is also very important. For example, in this like a previous immunological work, people have shown that for the hydrogel, if you vary the modulus between these two levels, both are already very soft, right? 1 kilopascal and 50 kilopascal. And then do the same kind of implantation experiment as we did. The foreign body response from these two modulus level actually still show a big difference, with the lower modulus giving a much lower foreign body response. So that means for the electronic materials and devices, we need to be able to get to that modulus range, very soft, similar to the tissue level. But if we take a look at the current status of the modulus for different kind of reported electronic materials and the devices, including the ones made with the semiconducting polymers, they are still much more stiffer, like with a several order magnitude difference than the level of tissues or organs. So then the additional question is, how can we create new designs? For example, design that mimic hydrogels to minimize or remove this gap, making the electronic devices move into this range. So then to do this, one work that we had been doing also started from the material level to make the semiconducting polymer into a hydrogel design. So basically, the main challenge that we had to solve is for semiconducting polymers, like 99% of them, especially the high-performing ones, are not water soluble. So then their design are not compatible with the typical processing method for making hydrogels. So then to solve this challenge, we came up with a new processing method that led us to make a double network semiconducting polymer hydrogel. With the semiconducting polymer, you can see from this SEM image forming the nanofiber highly porous structure embedded in another porous structure of a polyacrylic acid hydrogel. And then that on one hand led us to decrease the level of Young's modulus compared to the NEAT's semiconducting polymer by about 2 orders of magnitude. And at the same time, for the electrical performance in transistors, it didn't really sacrifice the level of charge carrier mobility. Okay, so using this as the key material, we also further characterize the relevant immune compatibility study regarding the modulus influence in the context of electronic device. So what does that mean? In the electronic device, the semiconducting layer usually has a very thin layer on the surface. Then the question we asked is whether the very thin layer on the surface still influence the overall foreign body response. So the results is showing yes. And actually the influence is very big. So I'd like to mainly here highlight one comparison. That is this semiconductor polymer with a two varied cross-linking ratio. That's led to the two different level of a mechanical property, only different by one order of magnitude. And then the result of the implantation is showing that this is the higher cross-linking ratio with the college density right here. And then this is the lower cross-linking ratio. Even though they are just thin film there on the surface, but this modulus difference is creating major difference of the foreign body response. Okay, so this is showing the importance of achieving very low modulus for the electronic layers in the device. And besides the material work, we have also spent some effort in creating the full device design that can be compatible and have low modulus. So in this work, my student Yang has been able to show that if we introduce only a very a soft interlayer between a still relatively rigid functional layer at the surface and like a very soft hydrogel substrate, then he can achieve a very low modulus for the overall device level, like shown by here, similar to the hydrogel. And then again, when we utilize this like device design in the model system to characterize the foreign body response, it shows that for this device engineering, as represented by this bilayer hybrid structure, it can achieve similar level of immune response, like a scar tissue thickness, comparable to hydrogel. All right. So basically, that's all I have with this. Hopefully, I have shown that starting from the material design on the semiconductor polymers and then moving gradually to the device, we have a much bigger range of design space to introduce new properties, not just stretchable, but also like some more interesting properties like bioadhesive property, immune compatible property to eventually enable us to use those bioelectronics with very intimate and effective biointerfaces. So at least but not the end, I'd like to first thank all my group members for their really creative and hard works. They are really the true heroes making all this happen. I didn't get to collect any piece of the data. It's really all their works. And also our research has benefited tremendously from our fantastic collaborators and also the funding support from the different agency. And thank you very much.